everybody. Hopefully you're here for the English version of our newest webinar. And this one is about optimizing engine performance with some keys to modern injection. My name is Jimmy Dinsmore. I'm just going to moderate this. No one's here to see me. They're here to hear the knowledge of our presenter, which is Jérôme Carpentier, and he is going to take it away. Any questions, comments? We do have the chat wide open. We also have Q&A open. Feel free to use either. We'll probably hold all those till the end, but feel free to put them in as they come up. And a reminder, you will get a certificate from us if you stay through the whole thing. We'll be emailing that out to you. I'm going to be quiet, and Jerome's going to take it away.
All right. So hello, everybody. So today's webinar is about homogeneous and stratified fuel injection. And that's funny because we just like to engage and talk with instructors or even field technicians just to see like what type of content they want to hear about us in our webinars and stuff. And we feel like this part with GDI engine and Stratify, something that worth learning about and talk about. So we're gonna talk and see exactly what we mean by air-fuel ratio. What is those type of combustion that we can have into those GDI engines, and what are the advantage and of course the disadvantage of different type of combustions. So air-fuel ratio, basically, like we all know, there's like this stoichiometric where it's like 14.7 to 1, so 14.7 ratio of air to 1 of fuel. And as we can see here into the diagram, we have that flammability range where, of course, the combustions can basically light it up and create some combustion into our engine and make our vehicle move, right? And we have our inferior limit here that the combustion is not possible, as we have the superior limit at the right. And again, that combustion is not possible. So whenever we have too much fuel for the air or too much air for the fuel, we are now in both situations where inside the engine, it's no more possible for the mixture to be lighted up and create that explosive action that's gonna move our pistons. So basically, our vehicles, our computers, our sensors monitor everything and really try to stay into that flammability range where we're gonna have some action going on inside the engine. And speaking of, we have all this term, what exactly is the superior limit or the inferior limit, and stoichiometric, lambda, type of mixture. So basically, our superior limit, unlike the traditional air-fuel ratio, we are talking about 12 to 1. So basically 12 of air versus 1 of fuel. So we're gonna be into a rich mixture where we have too much fuel inside our mixture. And the difference is with lambda, we are now talking about, let's say 0.8, and the lambda formula basically is the actual air-fuel ratio divided by the stoichiometric air-fuel ratio. Stoichiometric air-fuel ratio being 14.7 to 1. So that is going to be telling us what exactly our lambda stands for. Normally on lambda, when we are talking about 1 is the ideal or stoichiometric mixture. And if we are more than 1, then we start building up and become lean. So basically we have too much air than we're supposed to. And of course, there's some advantage of being lean or being rich, but there's also disadvantage. This is exactly what we're going to talk about today. Some Honda engines, for example, can be lean burn engines and operate to air fuel ratio as high as 22 to 1. And so basically, if we're going to look to that chart here, 22 to 1, we are way above our inferior limits. So if we go back to the schematic here, or the diagram, we are way into this zone where combustion is not possible. So how can those type of engines, or even Honda, for example, can manage to make it possible for a 22 to 1 ratio to be able to create that combustion inside the engine? So we know that combustion is all about air, fuel, heat, kind of create some combustions. Ideal complete combustions produce CO2, so carbon dioxide, and H2O, so water vapor. But in reality, we all know we cannot have that ideal perfect combustion. So basically, the combustion is partially incomplete, and then generate unburned hydrocarbons, so HC, so like particle of fuel, and CO, so carbon monoxide. And those polluants, sometimes they are not treated in our catalytic converter, so that pollutes like the environment. So did you know, this is something that we like to ask, did you know? So we just refer to basic stuff or basic fundamentals and more even advanced systems. The question, did you know? And we really want to start a series of webinar about that question mark, did you know? So today is, did you know about the gasoline direct injection engine, so GDI, that during a lean burn, the engines, the computers, like I said, with the sensors and stuff like that, they managed to go to some strategies like some stratified mode, and then into this mode, we need some more robust, for example, converter operation, because we do have an increase into NOx that's being generated by the combustion, and we need to treat those NOx. The TWC, or the three-way catalytic converter, does not do well on its own with a lean burn engine. So there's some strategy, again, or some more components, refined components, add to those engines to make it possible, and just follow all the regulation for all the pollutants and stuff like that. So we have different types of combustions. Basically, we have the most basic one, the stoichiometric homogeneous. So as we can see, we're going to have that type of injection when our engine is into the intake or the emissions. And basically, those bluish dots going to represent the air molecule, and those yellow dots going to represent the fuel molecule. And basically, we can easily see that the mixture is composed of both equal molecule, air molecule and fuel molecule. And like I said, those molecules going to be coming inside the chamber while the engine is into the emissions. Then we have the lean homogeneous. So basically, we have a mixture again coming inside the engine into the emission cycle. But then, as we can see, there's more air molecule than fuel molecule. And the last one that we're going to talk about is about lean stratify. So lean stratify basically is concentrate the fuel molecule close to that spark plug. So because of that locally concentration of those fuel molecules, we're going to be able to still have a pretty good combustion, or even still have a combustion, even if we have like a ratio that is super high in those air molecules. And the difference now is that this type of mixture is going to coming in compression, or it's going to happen into the compression. So the question is, why only on those GDI engine? That is some question that are often asked to us, like, what can I have that lean stratify type of combustion into like standard engine? And that's the thing. So we need to have that injection when the engine is into the compression mode. So we do need GDI engine because our injectors gonna be inside the chamber and not into the air intake. So that is why, yes, lean stratify strategy is only for those GDI engines. So some advantage and disadvantage of different type of combustion. So if we start with that stoichiometric homogeneous, it's the most widely used system. So we have seen it, we know it. Basically, it's super simple system, super simple design, nothing too complex. So we don't have that much cost related to those systems. Inexpensive, no flammability issues, no engine instability. The stoichiometric homogeneous is like the ideal combustion inside our engine, so everything should be fine. Also, it's going to allow the catalytic converter to operate at full capacity. So the converter is going to have enough air to do its job and treat all those NOx and HE and CO. But again, we have some disadvantage. So we have some pumping loss due to those homogeneous stoichiometric combustions. Pumping loss is related to the amount of air that can be injected inside the cylinder. And because we want to keep that stoichiometric ratio, we're going to have to create some restriction from the air to enter that engine, and we do it with the throttle body. So by closing the throttle body, we prevent too much air coming inside the engine, and we know that the engine is basically a vacuum pump in a way, and with the throttle body closed, then we have some pumping loss. So the engine is working and trying to fight that pumping loss. So basically, there's some energy loss in that concept. And we also have some thermal losses because like the mixture is stoichiometric, so it's perfect. All the heat generated by the combustion inside the cylinder basically is going to be even all the way to the cylinder. So the heat's gonna like be disappear in the cylinder walls. So we're gonna have some important thermal losses and energy losses also during that combustion type. Lean homogeneous. So basically we have much less pumping loss. So there's less restriction. So basically we want more air coming inside the engine or the cylinders. So basically that is why we have a less pumping loss. We can open up that throttle body, prevent that from happening. We do have a reduced fuel consumption. We all know that. Lower vehicle emissions, so less carbon monoxide and hydrocarbon. So unburned hydrocarbons, we don't have that since we have less fuel particle inside our mixture. But be careful, too lean can produce more NOx. So if we have a mixture that is way too lean, we're gonna create some locally super warm zone, and that's gonna create a lot of NOx. By creating that much NOx, our converter, for example, can be a bit not efficient to treat those NOx. So we do have less heat loss. So I know that if our mixture is lean, like I said, we're going to create more heat in some parts of the cylinders, but that's the thing. We have less heat loss since it's not like equals all around the cylinders, but it's really locally. And that is why we say that having an engine who's running too lean can be really, really hard on those components like pistons, valve, and stuff like that, because, like I said, the heat is locally. So the flames is going to hit some of those components and going to create like superheat point and can damage those components. The advantage now, we have reduce in combustion speed. So like I said, less fuel equals fewer reactive. And when we say that we have a reduction in combustion speed, basically the speed of which the flame is going to spread to the mixture inside the cylinder is going to be slower. And when we say slower, we mean like less powerful. So we do have a loss in that those power for the engine. And of course, we can have some engine instability because yeah, we do have some, like we said, reducing combustion speed and stuff like that. So depending on what's the charge on it or on our engine is, if we are going to the highway and we do want it to accelerate it, but our engine is for some reasons too lean, then we can have then engine instability. The catalytic converter, we no longer have enough CO or HC to reduce the NOx, so that's the thing. So we do have a lot of air, but because we don't have carbon monoxide or hydrocarbon, we cannot like split those molecules and like treat the NOx and generate some H2O, for example, in carbon dioxide. So now let's talk about the lean stratified now. So basically, if we have, imagine having a vehicle without like having GDI and stratified strategy. Basically, we can go to homogeneous, where we are super lean and we are inferior to the limit. So let's say we have like that Honda's 22-1 on a standard engine that couldn't be able for any combustions. So that engine wouldn't run at all. So that mixture where it's too much air is going to be like, of course, introduced into the cylinders when we are in admissions. But imagine we now have the GDI in Stratify strategy. What we're going to do is really locally push all these fuel particles close to that spark plug, and by doing so, where we're going to look around that spark plug, we're going to have now, even if we have globally having a 22-1 ratio inside our cylinder, we're going to have a much more lower ratio close to that spark plug. So for example, we can have like I don't know, 11-1, really locally close to that sparking plug. That's going to be possible for the engine now to create that combustions and run on a super lean ratio. So that is something that is really good about, really cool about that strategy, is being able to run super lean, but again being able to have some combustions. Precise fuel, of course, ensure that the combustion, while the excess of oxygen is going to exit the engine and it's going to go through the converter and can be stored for further NOx treatment, for example. So that again is a good thing. So if we look to that diagram here, so we have those different zones where we have the stoichiometric mode without AGR. We also have that zone where the engine is gonna be in stoichiometric and using the AGR. At the top here, we have the lean mode, and at the bottom in the green zone, we have the stratify mode. So what is important to see here into that graph is we have at the bottom the engine speed, and to the y-axis, we have the BME, so the brake mean effective pressure. What exactly is that? Is basically the force that's going to be applied to the distance to generate that rotation force. So if we look at that stratify mode here, we can really see that basically it's not good for all the scenarios, right? So we do want to be in stratify mode where the engine speed is quite low, and the of course the load on the engines is going to be also quite low. So, for example, we can be at idle or close. If we look to this zone here, so around 2,000 to 3,000 RPM, we can go to up to a 30 to 40% in fuel consumption. So it's a huge gain there. And so of course that's one of the strategy. But again, if we want to go and accelerate it and get some speed, we then go switching to a stoichiometric mode, because that stratify mode is no more an advantage for the engines to be run to. So what else the disadvantage of the stratify mode? Because we know that the biggest advantage of it is really fuel consumption. But what about the disadvantage? So we're talking about higher cost. So we do need some direct injections, so special injectors. We do need to have some different pistons, a different combustion chamber, injectors, complete emission control system into the exhaust to treat the NOx. So those components aren't cheap. So basically the cost related to that system is really high. The complexity is really high. And when we're going to go to how that GDI engine works, basically, like we said, we have that direct injection. The late injection timing is all about that strategy here with the Stratify. So like we said, it's going to be the late injection. So when we are in compression, the fuel is going to be injected to the piston here, and the piston have a special shape at the top that's going to redirect all the fuel or most of the fuel close to that spark plug here at the top. Even in some older generation of GI, they used to have 2 injectors, and again, the cost related to those systems is even higher. When we say like we need to have some in-cylinder movement, we are talking about piston design and airflow. Airflow is super important in those engine and that strategy here. And a really cool, like I said, type of engine that use most of the airflow to do the Stratify type of combustion in those engines is the Audi fuel stratified injection engine, so the FSI. So basically, in our intake manifold, we're going to have some rotor flaps that's going to be able to change the orientation of the air, and it's going to create some swirl and tumble. And here into that picture, we can clearly see what's swirl. So basically, we're going to tend to create that movement in the air where we're going to push everything up into the cylinder, and we're going to have that tumble where we're going to create that rotation where again we're going to push everything from the bottom to the top. So basically, during that compression again, we're going to redirect all the fuel close to that spark plug without necessarily having that different piston shape. So just by modulating the airflow inside the chamber, we can manage to redirect everything close to that spark plug. So if we're going back here, go back here, there we go. So like I said, all the strategy again is about having some lower fuel consumption, but again, we don't want to be only running lean, because that's going to create some problem with our engine, and we're going to have probably some problem also with the pollution that our engine's going to generate, and can be necessarily treated by our catalytic converter. So that is why we want to be into those lean mode, or even under the inferior limits, but not for too long, or not for all the scenarios. So that engine, Honda engine with 22:1, is only going to be available in a way, or activated, where the load, the charge, the RPM is like super low on the engine, and we don't need to have that much power with our engine. But the rest of the operation is going to stay the same, and we're going to be able to really be into those stoichiometric, or to the flammability range that we see in those diagram here. So the only moment that we're going to go under the limit is going to be when the charge on the engine is going to be lower, and we don't necessarily need to have it for now. But the rest of it is all about the strategy to get the more power, the more efficiency of our engine. So Stratify is really a strategy that we need to be able to really understand nowadays. So I don't know if there's any question in the Q&A, Jimmy?
Currently, there is not. I'm going to put, because Jérôme, first of all, let's give it up for Jérôme, because, I mean, as you can tell, English is not his very first language. So he did an amazing job here. I think you're up to, what, 4 languages you speak now, Jérôme? That's freaking impressive. I can barely speak one. I am going to put a link into the meeting chat, because I work in sales. So promoting our GDI engine bench trainer, which is one of our best sellers. And for sure, everything Jérôme talked about here, you can demonstrate at length on that trainer. So we weren't here to sell you that, but I'm kind of here to sell you that. So I dropped it into the chat. But if there are other, you're getting a lot of good jobs, by the way, in the chat. A lot of people said you did amazing and good job. We will we'll send a PDF of this entire presentation along with the chat, or I'm sorry, along with the recording of this, and later in the week you'll get your certificate of participation, which you can use towards your PE if your administration so allows it. Now's the time for questions. We have time. I think you either left them like stunned, dumbfounded, or you did such a perfect job that
I don't know. But Jimmy, you're right, and we do have some of our engine bench that can really demonstrate those Stratify strategies, since some of them are GDI, and I really wanted to have one for you guys today, but yeah, it's a little bit complex, and we need to use some scan tools and go to the live data to really see and feel why exactly those are strategy working on those engine. But this is a really good way, with all that theory, to show and demonstrate students how those strategy operate in a real life scenario, for example. So yeah.
Very good. So it doesn't. Oh, Can you explain more about how EGR flow and how it might influence stratified mode?
Yeah, so if we go back to our schematics here. So basically, what we want with AGR and without AGR. So basically, AGR, we're going to reuse those unburned fuel, can be from the combustions or can be vapor from the fuel tank that we're going to filter through the canister. So we are still like doing some fuel economy with AGR since we are using those vapor or unburned HC and CO from the last combustions. And then we are running leaner in a way. So basically, we're just going to replace those fuel particle, molecule, whatever that we use to inject with those unburned particles. But the thing is, again, the power is going to be a little bit less. We're going to run into, fuel. We're gonna run and gain some fuel consumption. The power isn't going to be that much high than a lean mode, but it's going to also prevent from having some pollutants out of the vehicle. Then when we're going to have more charge in our engines, or we're going to run up to speed, then we're going to kill the AGR since we do want to have all the fuel particle that we need. And those fuel particles going to be better for the combustions than just like unburned particles from the last combustion. So the stratified mode, like we said, is like the transition. It's another layer add to the AGR system that we are now familiar with. So basically, before Stratify and GDI, we did have only the EGR. Can be with those valve, purge valve, and stuff like that, or where's the intake and exhaust valve gonna be open at the same time at some point. But basically, before GDI and Stratify mode, we only had EGR. So basically, that green zone, basically that was nothing. And then we started with AGR and without AGR. Now we just had another layer, like we said, a layer where the fuel consumption is going to be, the gain on the fuel consumption is going to be way higher. It's just that at some point engineering, the engineer was like, hey, you know what? We have an opportunity to add something into that zone where we can really gain into the fuel consumption. I don't know if it answered your question.
I shared your email in the chat because a couple people said what if they have questions afterwards. So I know I speak for you. Your email's wide open, and anybody's free to ask him questions today, tomorrow, or weeks from now. There was another question that said, any PIDs that can shed light when suspecting carbon buildup on the cylinder head valves and or piston?
Well, that's a good point. It's going to depend, but I mean, you're going to see some instability. You're going to see some PDI like the engine temperature, because those carbon it's going to be like warming up and absorb all the heat from the like a lot of heat from the combustion, and it's going to create some super high heat zone in those engine, and you can see that with those PDI. So like I said, engine temperature or engine coolant temperature, you're going to be able to see that definitely. Yeah.
Well, it looks like you got everyone's questions answered. And should you still have more questions, like I said, Jérôme's email is right here. Believe it or not, he's got to do this all over again in about 10 minutes. He's going to do it en français this time. You can stick around if you want to learn some French. Otherwise, we want to thank Jérôme for his time and knowledge and expertise. He's a major asset to our team. So thank you, everybody, for coming. And thank you very much, Jérôme.
Thank you, everyone. Have a good day. Bye.